Okay, so this is just to show you the easier part, the reading of the data. We need to use the nibable library. And in this case, I just loaded a T1 with contrast enhancement. And what I do here is showing the central slices in the 3 axes. Notice that for better visualization, I flip and transpose some axes so that they are oriented in the way that we like, with the nose on the top, the hairs on the top, and the neck on the bottom, and things like that. I'm not rescaling the images in any specific way. But you will need to keep in mind, at least in some type of images that we will do in the next lectures, that there is no intrinsic intensity scale. This is something that I generally stress a lot. If we take a look at the images 240 by 240 times 155, all the images have been resized in the whole data set to have the same image. The vector will be, the tensor will be on the same shape for all patients. When we will implement some neural networks, that will be useful. This is not a given. It could be anything, because in any center you acquire with some dimensions. And also the sequences have different dimensions, number of slices especially. If we take a look at the minimum value, and well, the minimum value is 0, of course, because it's masked. The maximum value here is 1,200. As I said, MR images do not have any intrinsic scale, so it's not like with CT that we can say, okay, let's crop between -50 and 20. This specific subject is 1,000, another will be between 0 and 1, and another one will be between 0 and 1 million. So it's generally adjusted qualitatively. You can also play around with the other sequences just to look, to take a look at how they look like. And you will see that they've been perfectly aligned pixel by pixel. In the next part, I'm reading the truth image for the segmentation. I get the data this way. And for historical reason, in Bratz, the labels were numbered 0, 1, 2, and 4. The 3 was missing, so sometimes I remove the number 3. And then I did this calculation of the center of mass calculation just to extract the, yes, to extract for this specific subject where is the center of the segmentation, because if you go to the central slice, you won't see the mask. Instead, here, if I'm putting myself at the center of the segmented area, I get this, I do see something. The trick that I'm using here for visualization is showing my image slice, and then I show the mask using one other color scale and using the alpha parameter, which gives us some transparency. And also I'm setting all the 0 values in the mask as none, and PyPlot interprets not a number as transparent values, so we can get a decent visualization of this mask. Another option could have been to use the pyplot.contour function to achieve the same results. So, the same objective, not the same results, because with contour you get the boundaries of the segmentation. With IMShow and the alpha parameter, you get shading. Any questions? Okay, so the next task that you have is to, you can do that in multiple ways using pandas or vectors or whatnot. Anyway, you have two folders. One which contains LGG, means low-grade glioma, and one's GBM, glioblastoma, which is the high grade. So these are your two labels, your two categories, the two folders. You need to get lists of all the data. And then you can, using the help of this radiomic extractor feature, you can take a look at how it works first on a single subject. Then you can extract all the features and save them in a, and save them in a data frame for further classification tasks. By the way, here in the solutions that I will upload, I've computed the features on the T1 contrast enhanced sequence. You could you can try on other sequences. You can also try just maybe on the shape of the segmentation, just counting the pixels of the different categories, or just working on the shape features. Now, when you compute the features on a single subject, you can see the list of all the features that get extracted, and you can decide to compute only the ones related to shapes and not to textures. So it's up to your creativity to see how well can you go. Remember to split the data set in training and validation, and that's it.